The last thing we're going to talk about for this general topic of rank is a very important idea. It's a special case of a very important theorem called the implicit function theorem. Uh, and implicit here basically means implied. So this is like the implied function theorem. And the basic idea of this theorem is that a system of constraints implies a function taking values for dependent variables when we fix independent variables. So that sounds kind of opaque right now. So let's give an example that we've kind of already seen. We've already kind of seen a version of the implicit function theorem in action. We just didn't realize that this is something that could be said. So let's say we have our good friend, this example, that's followed us throughout our life. It's always been there for us to show us different interesting facets of linear algebra. Well, remember that this implied the constraints, right? So this was a linear system of constraints. So here are my system of constraints. Here's I've got a linear system of constraints, and that implies the parameterization of the solution set x3 is equal to -5, if you'll recall, and x4 is equal to 2. Well, this actually implies a function, right? So this is my independent variable, and these are my dependent variables. So this implies a function, f of x2, right? So if I know the value of x2, then I'm gonna pump out the values for x1, x3, and x4, and it's gonna be 7/2 minus x2, -5, and 2. Right? So here's what happens. Whenever I fix x2 for this function, I get values for x1, x3, and x4 that solve the system of constraints. And this is the implied function. This is the implicit function that I'm guaranteed by the implicit function theorem. Only we've got a system of linear constraints. You can have nonlinear constraints that are actually very complex, and this function still will hold, or this theorem will still hold. And we actually already have the tools to prove this theorem in our particular case, right? But there's a couple things to say. So I can get a solution in terms of x2, but I can actually maybe talk about using another variable as the dependent variable, right? And which variables are the independent? So in this case, we had that x2 was independent, and x1, x3, x4 were dependent. But what about if I kind of switch that up? Well, I could also have x1 as the independent variable, and then I would have x2, x3, and x4 as dependent, right? But what if I chose x3 as the independent, right? So x3 is independent. Can I do that? Well, there are two good reasons why that's not possible. Why I can't get a function of x3 so that when I put that function, when I put that in, I get a unique value for x1, x2, and x4, right? Well, first of all, the constraint x3 is equal to -5 means that there is no free domain for the function. That is, I can't just plug in any x3 and have a solution to the system. I can't do that because, of course, the system has to have that x3 is equal to -5 in order for it to be a solution. So that's one thing that kind of went wrong. The second thing that went wrong was our choice of x3 does not uniquely determine that should be an E, x1 or x2, right? X3 has no bearing on what x1 or x2 could possibly be. So that means that my function could have infinitely many values for x1 or x2, right? Well, I mean, it could have infinitely many values for x1, and then of course x2 would be constrained. But that means that my function, if it could take any x3, well, I wouldn't get a unique value over here. And I need to have a unique value over here to have a well-defined function, right? Now, I've been talking about independent and dependent because those are nice kind of easy concepts to understand, right? The independent variables are the things that are independent and I get to choose. And the dependent variables are the things that are constrained as soon as I fix the independent variables, right? These are my inputs and these are the outputs. But the terminology that's used in economics is endogenous and exogenous, right? So basically, to get translation mode going, right, we have that the independent is the same as exogenous. And that dependent is the same as endogenous. So the exogenous variables are, the variables kind of supplied to you for whatever reason. And the endogenous variables are the things that you have to figure out, well, what were they based on the inputs. So these are the inputs, these are the outputs. That's all that really comes down to. So now we have to be careful, because of this example, we have to be careful about what guys we pick, right? But we can characterize exactly what our exogenous and endogenous variables can be. And this is a theorem, right? So a theorem, I mean, it has a fancy name, theorem, right? And so this is the linear implicit function theorem. Linear version. So a theorem is just a really fancy fact. It's kind of a fact that's a really big deal, and it's kind of harder to demonstrate than just a simple fact. So the theorem is that for general system of linear constraints, and remember that system looks like A11 x1 plus A12 x2 plus ... plus A1n. So I have n many variables is equal to B1, and then I keep going for m many equations, and I have AM1 x1 plus AM2 x2 plus AMN xn is equal to BM, and I'm going to call this system star because I want to refer to this system again. So for a general system of linear constraints like this, there is a well-defined, that is, if I put in an input, then I get exactly one output, right? So there's a unique solution, right? Implicit function f of xm plus 1 not. So the not just means that it's, some fixed number, or some number other than just the variable. So I'm actually putting in some number here, plus 2 all the way up to xn. So these are my input variables, or exogenous variables. And on the other side, I'm going to get out x1 naught all the way up to xm naught. So this is my implicit function. So the x1 through xm are my endogenous variables for the system. So this is my implicit function, and that's going to exist, and it's going to be well defined. And in particular, this x1 naught, xm naught, well, the function is going to be such that. So this is the way the function is defined, and it's such that x1 naught all the way up to xm naught is the unique solution to we have this system. We'll call it, say, double star. M plus 1 here, xm plus 1, 0, minus, so I'm running out of a little room here, so dot dot dot, so minus dot dot dot, minus a1n, xn naught. So I have this system of equations. It goes through all the m many equations. A m1 x1 plus a mm xm is equal to bm minus am m plus 1 xm plus 1 naught minus dot 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 minus a mn xn naught. So this is a system. So the way I acquired the system is I took all the inputs for the endogenous or exogenous variables, and I subtracted them from both sides of all the equations. So then I have a fixed number. This is my new, you can think of this as a new b1, this entire term. This entire term is the new bm, right? And then I have a system that's dependent upon the endogenous variables x1 through xm, and the x1 naught up to xm naught that my function pumps out is the unique solution to this, if and only if we're running out of room here, but we're very close. If and only if this coefficient matrix a11, a12 up to a1m, am1, am2 all the way over to amm has full rank. Or equivalently, the thing is non-singular. Right? So we said a lot, so you should go back through this and listen to it a couple of times. And the proof is really simple. So I can use a system of endogenous variables if and only if the coefficient matrix associated to those particular columns, right, has full rank or is non-singular. Well, we have that full rank is equivalent to non-singularity by our previous facts. Which is in turn equivalent to star, double star, always having a unique solution for any right-hand side. And in particular, that's equivalent to this function being well-defined, and thus my function is well-defined, and I have it. So all these things are equivalent, and so we get the result.